Hello, and welcome to today's webinar on rupture disks. Rupture disks are safety devices designed to break reliably at precisely defined pressure levels. While modern rupture disks generally perform well, there are a variety of conditions and situations under which the integrity of rupture disks may become compromised and they won't operate as designed. When this happens, plant, equipment, personnel, and the environment are put at risk. During this webinar, you will learn about the selection and sizing of rupture disks, along with techniques you can use to troubleshoot the operation of your disks to ensure they perform optimally. My name is Scott Jenkins. I'm the senior editor with Chemical Engineering Magazine, and I'll be hosting today's webinar. And I have the pleasure of introducing the presenters today, Cam Holmes and Scott Muddyman with ZOOK. Cam is the Vice President and General Manager of ZOOK's Metal Division and has been for the last 13 years. And Scott was former president of ZOOK's Metal Division. He retired last year and is currently working for ZOOK as a consultant. During the presentation, if you would like to ask a question, please type it into the chat box on the left side of your screen. And also, if you have a technical issue, type it into the same box and someone will assist you. So with that, I'm going to turn it over to our speakers. Go ahead, guys.
Thank you, Scott. Hello, everyone. My name is Scott Muddyman, and I'm thrilled to be one of your presenters today. Thank you for taking time out of your busy day to join us this afternoon.
Thank you, Scott. My name is Cameron Holmes, and I also want to thank each and every one of you who've taken the time to join us today. It's great to have you with us. My colleagues sitting beside me here and I have over 50 years of combined experience in the rupture disk industry, and I can tell you that every day we're learning something new. This small, simple-looking device is actually significantly more complicated than it looks, and our goal today is to try and pass on some of our knowledge and to help you understand some of the basics with these devices. Before we start to discuss what you need to know about selection, sizing, and troubleshooting, I want to provide a quick introduction to rupture disks. First off, what is a rupture disk? At its simplest, a rupture disk is a safety device. It's actually a pressure relief safety device, one that is typically custom designed to protect plant, personnel, and equipment from unplanned or unexpected overpressure. That's a fancy way of saying it's designed to stop things from blowing up. It's generally a one-time use, thin diaphragm designed to rupture or burst at a designated pressure. What does a rupture disk actually do? Well, a rupture disk is a differential pressure device. A proper rupture disk assembly creates an impermeable barrier in a pressurized system, and it bursts or opens when the differential in pressure across it reaches a designated level. We have a quick video to show you demonstrating rupture disk functionality. Here you can see a rupture disk mounted to the end of a chamber, which is sealed at one end and a rupture disk mounted on the other. Pressure is introduced into the chamber and the disk bursts or opens when the pressure differential reaches a set point of the disk. Differential pressure simply means the pressure on one side of the disk is higher or lower than the other. If we pressurize both sides of the disk equally, nothing would actually happen. Here's another example using water. Rupture disks are custom designed safety devices, and they can be engineered to function in both gas or liquid service, what we call compressible or incompressible service. Compressed gas has significantly more stored energy than liquid, and the burst event is much more violent. In terms of rupture disk design, a gas burst poses significantly more challenges to rupture disk engineers. A simple way to explain what a rupture disk is and what it does is to understand that a rupture disk is to a pressurized system what a fuse is to an electrical system. It's a one-time use pressure relief safety device.
Rupture disks have been around for a very, very long time and have earned a solid reputation for successfully protecting all types of pressurized equipment. The original rupture disk was simply a piece of thin foil clamped between a couple of pipe flanges. Designed to be the weak point in the system, as the internal pressure increased, the foil yields because it is thinner and therefore weaker than the vessel wall, eventually failing to safely relieve the overpressure and protect the integrity of the system. It was simple but very effective. The first patented design was in the early 1930s and is still produced by all manufacturers today. It built on the simplicity of the original disk design, adding 2 features to improve functionality. A reusable holder was introduced, improving burst repeatability by holding the metal foil consistently and providing a better, more reliable seal between both the disk and the holder and flanges. It also included factory pre-bulging of the disk foil to improve cycle resistance and reduce fatigue. The design is simple and fail-safe, relying on the tensile properties of the foil to control the bursting pressure. Since that first design, manufacturers worldwide have been working on new modern designs to address demanding application found in today's modern processes.
What are the advantages of rupture disks? Why even use a rupture disk at all? Well, first and foremost, for safety and protection. Protection of equipment, plant, and personnel. Pressure and pressurized systems are all around us, and an overpressure situation can be extremely dangerous. You just saw 2 very small volume, controlled demonstrations, but you can easily see the effects of release pressure. Rupture disks are passive devices with no moving parts. Rupture disks provide leak-tight seals and are available in a wide variety of corrosion-resistant materials. Rupture disks are low-maintenance devices with very high reliability. They are a time-tested, tried-and-true safety product. Rupture disks are extremely fast-acting, typically going from closed to fully open in less than 3 milliseconds. Rupture disks are a very effective, low-cost solution to a pressure relief requirement. There's another method of pressure relief that most of you may be aware of, and that's a pressure relief valve, also known as a safety relief valve. A safety relief valve is typically a reclosing device. Why would you therefore ever use a rupture disk instead of a relief valve? Well, first and foremost is cost. Comparatively speaking, rupture disks are very inexpensive versus valves, especially in larger sizes or when exotic materials of construction are required. The second is leak. Valves by their nature can leak, which can be a problem in some services. Rupture disks, however, are virtually leak-tight. They're basically a solid barrier with leak rates at the molecular level easily achieved. There are many cases where a relief valve is actually the preferred method of pressure relief. The most common would be in processing or continuous service applications, where downtime is a problem. A valve will typically reclose after relief, whereby a rupture disk would need to be replaced prior to restartup. A common application is actually to use a rupture disk in series with a relief valve. In this case, the disk is placed below or in front of the valve, in essence, isolating the valve from the process. The inexpensive rupture disk is the only thing exposed to the process until an actual overpressure occurs. This is extremely advantageous in highly corrosive applications. This combines the advantages of a fast-acting, leak-tight rupture disk below and the reclosing functionality of the valve above. Also, depending on the disk model, the valve can also be tested in place without removal, saving significant downtime and cost. There are, however, sizing-related challenges when combining the 2 types of pressure relief device that will always need to be considered, and we'll address them when we touch on sizing later in the presentation.
As you can see, there are many, many different designs to choose from, which can be intimidating for engineers to select the best design for their application. In an effort to simplify the selection process, we'll try and build a family tree that groups similar designs. For this webinar, we're going to keep it simple and limit the discussions to widely manufactured designs and not custom hybrid designs. The first division is based on material, either metal or graphite. Metal designs are divided into forward-acting or reverse-acting. The common characteristics of forward-acting disks is the foil the disk is made from is placed in tension when exposed to the system pressure. Burst is initiated when the tensile properties of the foil are overcome by the system pressure. For this reason, they are also known as tension-loaded disks. There are several variations of forward-acting designs available that are tweaked to offer better cycle resistance, burst control, or limit disk fragmentation, but they're all still considered forward-acting disks. The common characteristics of reverse-acting disks is the foil the disk is made from is placed in compression when exposed to the system pressure. To do this, the foil is first factory pre-bulged into a dome shape and installed with the system pressure acting on the convex side of the dome. Burst is initiated when the disk dome is overcome by the system pressure and collapses, opening along scores in the foil, shear rings, or knife blades. These disks are also known as compression loaded. Again, there are several variations of reverse-acting designs available that are tweaked to offer increased available burst pressure range, tighter burst control, or for compressible or incompressible service. It should be noted that compression loading of the disk allows the highest cycle life at operating pressures up to 95% of the marked burst pressure without increasing fatigue or nuisance bursts. Extra care needs to be taken when selecting reverse-acting disks, as some designs are not fail-safe. Incorrect selection or installation can lead to a dangerous situation. Reverse-acting disks tend to be more susceptible to damage and are typically designed for either gas or liquid service. Graphite disks are made from naturally occurring black graphite that is simply machined into a rupture disk. The first thing to know about graphite is that in its raw state, it is essentially a black carbon sponge with approximately 13% porosity. To remove the porosity and create impermeability, there are two processes undertaken by ZOOK. Resin impregnation is the first and most common process used. Various resins have been used over the years, but typically are either phenolic or furane-based. Through a process that includes pressure, vacuum, and temperature curing cycles, the graphite pores are filled with a cured resin that renders the graphite material impervious and suitable to use as a graphite rupture disk. Resin-impregnated graphite provides good corrosion resistance, inert material with non-ion contamination, temperature stability, and predictable results. A patented fluoropolymer sintered process involves preparing the graphite substrate to accept the fluoropolymer in the form of both liquid and powder. The coated graphite is then sintered at high temperatures that produce a highly bonded coating to the raw graphite, resulting in an impervious material. In addition to all the resin-impregnated graphite features, the fluoropolymer sintered process has greater corrosion resistance, higher operational temperatures, FDA approval, and a non-stick finish amongst its benefits. As you can see, selecting the best possible rupture disk design is not a simple task for any one person to tackle on their own. Good collaboration between the end user, system designer, and disk manufacturer is essential in getting it right the first time. Every application has both common and unique criteria that will guide the selection process. Common criteria include the following: vessel maximum allowable working pressure, or MAWP, specified burst pressure and temperature, marked burst pressure, manufacturing design range, normal system operating pressure, operating ratio, and rupture tolerance.
I want to take a minute to point out that we often do product training and factory schools for clients, channel partners, and employees. And this section of the training normally takes 4 to 6 hours. We could literally spend an entire day going over industry definitions, rupture disk terms and models, and the methodology for selecting rupture disks. For the purposes of this presentation, we'll only be reviewing the key parameters. First off is maximum allowable working pressure, or MAWP, defined as the pressure limit of a vessel as determined by the manufacturer. Any pressurized system that a rupture disk will be protecting should be rated with an MAWP. ASME, or the American Society of Mechanical Engineers, is the governing safety body in most of North America, and their boiler and pressure vessel code defines MAWP as the highest permissible gauge pressure of the vessel. A rupture disk chosen as the primary relieving device cannot have a marked bursting pressure greater than the vessel MAWP. Choosing a burst pressure below, even well below the MAWP is fine, but above is not. It should be noted that choosing a rupture pressure lower than the MAWP will result in a larger size during sizing calculations. As such, the MAWP forms the basis in the pressure setting and sizing for the rupture disk. Specified burst pressure, defined as the desired burst pressure of the disk as supplied by the end user. Simply stated, this is the value as specified by the end user as the pressure at which the rupture disk should burst. Typically, a process engineer will have determined the specified burst pressure in their overall system design calculations. This is the critical value provided to a disk manufacturer. Marked burst pressure, defined as the nominal burst pressure of a rupture disk as marked on the tag, also known as tagged burst pressure. This indicates the pressure at which a disk is designed to burst. The marked burst pressure is not always equal to the specified burst pressure because of something called manufacturing design range. Manufacturing design range, or MDR, is defined as a range of pressures within which the marked burst pressure must fall. Or more specifically, ASME roughly defines the MDR as a range of pressure within which the marked burst pressure must fall to be acceptable for a particular requirement as agreed upon between the rupture disk manufacturer and the user or his agent. This is the exact point in our product training seminars where we start to lose people. It's often hard for people to understand, why is the rupture disk that I ordered not marked with the pressure that I asked for? To explain this, I need to dive a little deeper into how rupture disks actually work. Remember, they're differential pressure devices that are ultimately relying on the tensile properties of material to function. Most manufacturers are sourcing their materials from vendors. ZOOK actually fabricates some of its own disk material, but in most cases, various thicknesses and grades of material are purchased from steel mills, etc. When this material is produced, there are tolerances. Tolerances in thickness, tolerance in chemistry, tolerance in yield strength. All of these variables lead ultimately to tolerance in tensile properties. In the case of metal disks, raw material is typically supplied in coil or sheet form. Two separate heats of material will never be exactly the same. Even within an individual coil, the left side could be microscopically thinner than the right, the start slightly different than the end. Seems insignificant, except when you're trying to fabricate a repeatable pressure relief device reliant on consistent tensile strength. All disk companies have their individual methods for manufacture, their own recipes to engineer opening and set pressure. However, disk manufacture is still very much a trial and error process. To make a disk to very specific parameters often requires fabrication, testing, and then equipment adjustment to get exacting burst pressure performance. When we make a disk for you here at ZOOK, our technicians have detailed procedures and work instructions on how to make your disk. However, often the disk will burst high or low during provisional testing, and adjustments need to be made in order to move or adjust the set point. Obviously, the wider the range of acceptable or passing tests, the easier it is to fabricate, and therefore the less expensive to produce. This range of acceptable pressures is called manufacturing design range. To put it another way, imagine I'm kicking a soccer ball into a goal. I'm not very good at soccer, but if the goalposts are set very wide, even I could score a goal in a few attempts. However, if you narrow the goalposts, it's going to take me more attempts to dial in my accuracy. Manufacturing design range is simply defining the width of the goalposts. The wider the posts, the easier it is for the disk manufacturer to produce the disk. The narrower, the more difficult and more expensive. Next up, operating pressure. defined as the normal system or process pressure. Simply put, the standard operating pressure the disk will typically be exposed to, or the normal pressure within your system. Operating ratio is defined as the ratio of operating pressure versus the lowest possible marked burst pressure, or what percentage of the lowest marked burst pressure possible with an agreed upon MDR is the system typically operating at. A critical factor in disk type or model selection. All rupture disk models come with a recommended maximum operating ratio. Because of materials of construction, disk geometry, and style, all disks are not created equal. Some perform much better when the operating pressure is high versus the marked burst pressure. Rupture tolerance is defined as the allowable deviation from the marked burst pressure. Once again, getting back to the material tolerance discussion, no two disks are exactly the same. Therefore, disks are produced with a rupture or burst tolerance around the marked burst pressure. Typically, for all disks above 40 psi, this tolerance is plus or minus 5%. There are manufacturers and disk models with tighter or wider rupture tolerances, and there are very specific tolerances for pressures below 40 psi. But suffice to say that every disk manufactured, tested, and sold is supplied with a stated or published rupture tolerance. So let's see a couple of examples of how this all fits together. First off is what we call a zero-range MDR example. In this case, let's assume the client has a system with an MAWP of 150 psi. Their process engineers have specified a burst pressure of 100 psi, and their normal operating pressure is 75. They've decided on a 0% or a zero manufacturing design range. This means that the marked burst pressure of the disk equals the specified burst pressure, in our case, 100 psi. The disk selected has a rupture tolerance of plus or minus 5%. In other words, the disk will be marked and tested at 100 psi. Each disk will burst somewhere within a pressure range of 95 to 105 psi. The disk will be exposed to an operating pressure of 75 psi versus a marked pressure of 100, which is equal to an operating ratio of 75%. This ratio will drive disk model selection. Next up is the exact same installation, however this time with a wider MDR of minus 10%. The MAWP is still 150, the specified burst pressure is 100, and the normal operating pressure is still 75. They've decided, however, on a minus 10% manufacturing design range. This means that the marked burst pressure can be anywhere between the specified burst pressure of 100 and 10% less than this, or 90 psi. These are the goalposts I was mentioning earlier. The client needs to expect disks supplied from the disk manufacturer with a marked burst pressure anywhere from as low as 90 psi to as high as 100. Typically, the marked burst pressure is the result of the average of provisional factory burst testing. Let's assume for this example that the lot qualification tests at the disk manufacturer resulted in an average burst of 95 psi, and this now becomes the marked level. The disk selected still has a rupture tolerance of plus or minus 5%, which means that each disk marked at 95 will burst within a pressure range of 90.3 to 99.8 psi. The main difference with this wider MDR is the calculated operating ratio. As acceptable disks could be marked as low as 90 psi, we need to use this worst case value when doing our calculations. The disk will still be exposed to an operating pressure of 75, but now the operating ratio is determined versus the lowest potential marked value, or 90 psi. This equals an operating ratio of 83.3%. This higher value than the zero range example could result in the need for alternate disk models.
So let's see how this all fits together. This slide is an example of a simple decision tree that goes through the decisions you must make and the information you need to have to select the correct rupture disk for your new application. I emphasize new because the process is slightly different when troubleshooting an existing application that may be underperforming. The first step is to gather all the information you can, both general and specific to your application. Next, you need to get your calculator out and work out the application operating ratio. At this point, you can start to filter out some designs based on their general information you gathered and calculated in the previous steps. It's really a process of elimination. Operating ratio. Eliminate designs that can't handle the calculated operating ratio. Fragmentation. Eliminate designs that don't meet the fragmentation requirements. You should now have a short list of potential designs. This is the point you need to look at the specific attributes of your application and decide how they affect your shortlist designs, and eliminate the ones that don't comply for one reason or another. Some of the considerations are: medium, compressible or incompressible. Eliminate designs that are not available for your specified medium. Burst pressure. Eliminate designs that are not available at the desired burst pressure. Size. Eliminate disks designs that are not available in the specified size. Burst temperature. Eliminate designs that are not available at the desired burst temperature. One last check to make sure you've not overlooked anything, and you're done.
The earlier on in the design stage that you can involve the disk manufacturer, the better. A collaborative disk selection process will result in the most efficient and optimum pressure relief solution.
Rupture disk devices are accepted by various national and international codes as a means of protecting a pressure vessel against an overpressure. These codes all provide guidance on generally accepted formulas and approaches. Proper sizing of a rupture disk device is as critical as selecting the proper disk design. Undersizing will allow the pressure to rise to unsafe levels because pressure is being created at a rate faster than is being vented. Oversizing is equally dangerous because the device may not open as intended, limiting the device relieving capacity. This is particularly true with reverse acting disks that require minimum amounts of burst energy to open the disk as designed. There are two recognized sizing methods. The first, known as coefficient of discharge, employs a fixed value known as KD to calculate a theoretical flow rate for a given size. This method is also referred to as simple sizing and can be used when the following conditions are true. The inlet and outlet piping are at least the same size as the rupture disk device. The device is located within 8 pipe diameters from the vessel entrance. There are less than 5 pipe diameters of outlet piping, and the design discharges directly to the atmosphere. ZOOK offers a web-based sizing tool to assist with simple coefficient of discharge sizing. The following video demonstrates a few of the main features of the program.
What you see now is the sizing project. The project is designed to contain one or many individual sizing calculations. The project ID is assigned by the program once I've clicked on Save, and I've also filled in fields to show the project name, customer reference, project date, and some notes. By clicking here where it says Sizing 1, I can begin the first sizing within the project. I'll start by filling in the tag number field by typing in a PSE number. Notice that here on the side, you can now see your tag number referenced. The revision number field can also be filled in with whatever reference you would like, and its entry will append to the tag number displayed on the left. Next, we have a choice to solve for either MNFA or capacity. MNFA stands for minimum net flow area. If you choose MNFA, you can enter the capacity values, and the calculator will show an MNFA result. If you choose capacity, you will enter the MNFA value, and the calculator will show a capacity result. For this example, we'll solve for MNFA. Sizing code is the next line, and the Z-size offers 3 calculation standards: API, ASME, or ISO. While the required information is very similar, the 3 codes do use slightly different formulas for their calculations, which we will see displayed later in the printout. Next, we can choose the fluid state. The 3 options are gas, vapor, liquid, or steam. The combination of sizing code and fluid state will determine which of the standard formulas Z-size will use in its calculations. All of the calculations in Z-size are based on a sizing method using coefficient of discharge, also referred to as KD. The next line has fields for purpose and relieving case, and the combination of these choices will set the overpressure allowance on the next line. The next line is where we will enter the required capacity. There are several units of measure to choose from depending on the fluid state, gas, steam, or liquid. In this example, I'll use 25,000 pounds per hour. Next, I can enter the burst pressure, which is the set burst pressure of the rupture disk. Clicking here where it says PSIG, you can see there are several choices for pressure units. For this case, let's use 100 PSIG. Here's where we can enter the burst temperature. This should represent the temperature in combination with the burst pressure at which the rupture disk should be expected to burst. Now we can look at the fluid properties. Since we've selected gas as our fluid state, we have a selection of several common gases. Choosing a medium will also show the corresponding values of that particular gas for ratio of specific heats, molecular weight, specific gravity, and density. Now on the right side, we can see the results of the sizing calculation. Since we're solving for MNFA in this example, ZSize has calculated the required MNFA is 3.876 square inches based on all of our information entered in the left pane. In the unit of measure dropdown, you can also choose centimeter squared or millimeter squared. Here, by equivalent diameter, the calculation is simply converting the MNFA in area to its equivalent diameter. In this section called Enter Disk Specs If Known, we are giving you the opportunity to enter the MNFA of your own rupture disk, and ZSize will calculate the resulting capacity. Calculation is using all the information that's been entered on the left side. So if I enter 5 inches squared, the calculation result is 32,247 pounds per hour. Here again we have the drop-down fields that give some flexibility to enter different units of measure. Next, I'll show you how to add, copy, or delete individual sizing within a project. Over here on the left at the top, you'll see two icons. The first is a plus sign that simply adds another sizing to the project. And the second icon is for copying a sizing. If I click on the copy icon, we now have a line that is an exact copy of the first one. Here we can change any of the fields to evaluate the impact on the size calculation. For example, I'll change 25,000 pounds per hour to 30,000 pounds per hour, and the resulting MNFA changes from 3.876 to 4.652. Here at the right top corner of the screen, you'll see icons for print, save, save and exit, or exit without saving. If I click on Print, ZSize will generate a calculation sheet with the information from your sizing entries and the results. It will open on a separate tab in your browser, and from there you can select your print options. Now I'll click Save and Exit, and that will bring us back to the main screen. Here we can see that your sizing project has been saved to the database. At this point, if you're finished, you can log off or simply close your browser, and your sizing project will be saved for the next time you log in. Thanks for watching the video on ZSize. Please contact ZOOK if you have any questions regarding ZSize or your rupture disk application.
ZSize is a great tool that can be accessed by anyone from a link on our website. Please take it out and give it a test drive. It's a great program. The second sizing method is resistance to flow and differs from coefficient of discharge because it considers all piping components in the relief system. The KR value of each component is summed to develop a system KR. The system KR is then used to calculate the capacity of the entire relief system. Sounds simple, but a complete knowledge of the complete relief system is a must. Typically, this method is used when the coefficient of discharge method does not apply. Caution should be taken when selecting rupture disk designs based solely on a low KR, as this can lead to a smaller diameter relief line and limited options to correct the situation if changes in the disk design are required in the future. Vendors can offer useful advice and sizing assistance, but ultimately the responsibility for sizing lies with the end user. The takeaway here is right sizing, and to provide right sizing, a collaboration between the user, process engineer, and the disk manufacturer is essential no matter what method is selected. Cam mentioned earlier an application that includes a rupture disk device in combination or in series with a pressure relief valve. For this application, the sizing is based on the pressure relief valve, and the effects of the upstream rupture disk device are accounted for by using a default 0.9 combination capacity factor, or CCF, to the sizing calculation to make the appropriate changes to the rated relieving capacity of the combination. The default 0.9 CCF value can be used for any combination of rupture disk device and pressure relief valve. A rupture disk or pressure relief valve manufacturer may opt to test a specific combination of designs to establish a certified CCF for that specific combination, which can be used in lieu of the default 0.9 factor. Typically, certified CCF values are higher than the default, but caution is recommended not to select too high a certified CCF value, as this can paint yourself into a corner if changes to either the rupture disk or PRV design is required in the future. For resistance to flow sizing, the additional rupture disk device is accounted for by simply adding it as another component in the relief system. Because a rupture disk is a differential pressure relieving device, pressure cannot be allowed to develop in the space between the two devices, and a pressure gauge, tri-cock, free vent, or suitable telltale indicator should be installed to permit detection of disk rupture or leakage.
It's important to remember that a rupture disk is a device that's designed to burst. Some people say it's designed to fail, but we like to say designed to burst or activate at an exact point. But like any engineered mechanical device, things can happen to affect performance, and this is when disk manufacturers have to use some detective work. First and foremost, rupture disks will not last forever. They're tensile devices exposed to various forces, temperatures, etc., and therefore they will fatigue. Sometimes bursting low or early is simply a case of service life. Another cause of fatigue can simply be operating ratio. It's important to understand marked burst pressure versus specified and manufacturing design range to ultimately know what pressure level of disk you will receive. We've had many cases whereby a client suddenly experiences performance problems, and the cause are simply that the latest lot of product has been marked at the low end of an agreed upon design range. Remember the minus 10% MDR example from earlier on. In this case, the specifications need to be reviewed in order to ensure the disk manufacturer is producing a product that will ultimately work in the field. This could result in a disk model change, but it can often simply result in a slight specification adjustment. Why do rupture disks fatigue? Well, the reason is that they're solid-state devices with no moving parts. As such, by design, they have no built-in safety margin. This is at the same time both a blessing and a curse, as the lack of safety margin is what makes a rupture disk fail-safe, but it's also what gives a disk a limited service life. Rupture disks are engineered products, but they can be delicate and fragile. Especially with reverse-acting disks, any minor damage to the disk dome will negatively affect performance and cause the disk to burst or collapse low. All disk manufacturers will take extreme care to fabricate, package, and ship you their disks, but handling in the field is just as critical. Disks should always be handled by their edges or tags, never touch the disk dome. A disk showing signs of damage should not be installed. Disk damage in the field is the single largest cause of nuisance bursts. I use the term nuisance burst loosely, and what I mean is a burst at a level lower than marked or expected. These nuisance bursts can still be expensive or result in significant loss of product or time or both, and they need to be avoided. We had a situation a while ago whereby a client contacted us because they were having performance problems with a competitive product. Namely, they were experiencing nuisance bursts. The problem they had was that their equipment was very remote and unmanned. Every time they had a burst event, they had to send a crew out for an expensive repair. They simply thought there was an issue with the disk design and performance. What it turned out was that in order to reduce cost, similar to the assembly on the left, the inlet side of the holder had been reduced to a point where the disk dome now protruded beyond. This can pose problems during installation, as it's easy for the disk dome to be impacted during handling or insertion. Sometimes the damage can go undetected. This is exactly what was happening. Our solution shown on the right was simply to provide an assembly with a similar disc style, but with a pre-torque holder that sealed the disc and fully protected the dome. There hasn't been an issue since. It's important to realize that a rupture disc assembly is typically just a joint or a connection point in a pressurized system. All rupture disc manufacturers have recommended torque levels for their designs. Following these instructions is critical to achieve a leak-tight connection. Some disc designs are extremely torque sensitive, and incorrect torque over or under can cause disc damage or leaks. Most rupture disc assemblies utilize gaskets to seal the device into piping. Therefore, gasket style, and more importantly, gasket integrity, is a critical component in ensuring a proper seal. Misaligning holder and disc components or incorrect torque patterns can also cause leaks. Similar to changing a tire on your car, it's important to gradually increase the torque around a flange in order to provide equal loading to the assembly. Misaligned piping like that shown in this picture or incorrect flange torque can result in multiple leak locations across a rupture disc assembly. Some manufacturers offer pre-torque holders, which allow the installer to preload the disc and create a leak-tight seal prior to field installation. There are various methods used to seal rupture disc within the assembly. This varies from manufacturer to manufacturer, but it can include O-rings, pinch points, welds, metal bites, etc. Care should always be taken when handling holder sealing surfaces, and they should be inspected every time a disc is changed. Any damage to a sealing surface can cause a leak. In this picture, you can see that the raised sealing bite section of a holder has been damaged, which could create a leak path in the assembly. Not all holders or disc assemblies are suitable for every situation. If you're confident that your discs and holder sealing surfaces are not damaged and that you're following proper installation procedures, then you should contact your disc manufacturer for help. What can you do? First of all, have the installation history at hand. Is this a new or existing installation? How long has a disc been installed? Have any of the process conditions changed? Valves, fittings, piping, etc. Have the problems begun with a recent shipment of product? Take pictures, plenty of pictures. The disc, holder, flange setup, upstream of the assembly, downstream, all valuable information in diagnosing problems and engineering solutions. Have the lot number of the disc at hand. All manufacturers use lot numbers to control batches of product. This is critical for fabrication investigative work. Contact the factory. Go through your channel partner, go through your sales office, whichever is the normal method of contact for you, but ultimately your issue should make its way back to the factory. All disc manufacturers will have quality and technical support people available to help you. They will all take performance issues with their respective products seriously. We're all in the business of making safety products, and we take that responsibility very seriously. But please understand that remotely analyzing or forensically diagnosing performance problems is difficult for disc manufacturers to do alone. We need your help. It's rarely the disc's fault. It's simply reacting to its environment, and it's up to both of us to figure out the best engineered solution.
People ask us all the time, how long will my rupture disc last? The truth is, nobody knows, and scheduled preventative maintenance is recommended, or when the process is already down, change the disc out. In the absence of actual installation history, we suggest starting with 1-year intervals between scheduled maintenance disc replacement. I understand how self-serving this sounds, but if you want to get out in front of it, be proactive. The cost of replacing a relatively inexpensive disc is far less than the cost of an unplanned shutdown and the resulting loss of product and production. There are no specific maintenance tasks that can be performed on a rupture disc device, with the exception of pre-torqued holders. If a metal rupture disc device is taken out of service and the disc removed from its holder, it should be replaced. Holderless graphite discs can be reinstalled after inspection. Pre-torque holders with integral pre-torque bolts can be removed from service, inspected, and reinstalled safely because you're not disturbing the seal between the disc and holder. You are taking out the whole structure and putting the whole structure back in after instruction. During disc replacement, personnel can perform maintenance tasks on the rupture disc holders. First, the holder's gasket surfaces should be examined for foreign material. Any adhered gasket material from previous installations should be cleaned from the gasket surfaces of the holder thoroughly. Dirt and grit on these surfaces can cause leaks. Next, the seat area should be inspected for scratches, dents, or nicks, because imperfections on these surfaces can also lead to leaks. Care should be taken not to introduce any new scratches to the seating surfaces. A clean cloth with a suitable solvent can be used to remove residue. If that does not fully remove it, fine emery cloth or steel wool can be used, with caution not to damage the surface by pressing too hard and making grooves or scratches in the sealing surface. If scratches, dents, or nicks are still present, contact the vendor. Do not machine or modify the holder. No one wants to have a rupture disc. They need to have a rupture disc. It's a safety device. When a rupture disc does its job, suddenly, some process is down. Do you want to change it when the disc decides, or do you want to change it when you decide? When your fuse blows, you can't cook your dinner. You don't want to have fuses, but you must have one, or you can't cook your dinner. In closing, all rupture disc manufacturers offer good quality products that will work as intended, provided they are selected, installed, and applied correctly. We need your help to ensure all of these things happen. Thank you for listening this afternoon.
I also want to thank all of you for your time today. I hope we've managed to increase your understanding of rupture discs. And to echo what Scott has just mentioned, a collaborative effort between yourself and your rupture disc manufacturer will ensure a proper sized and engineered solution to your pressure relief requirements. Thanks again.
Great. Thanks, Scott and Cam. This is Scott Jenkins again. We do have some time at the end for a question and answer session, and so we'll get to those. So the first question is, are rupture discs sold at standard pressures, or are they custom made to order?
Well, I'll start with that one. The answer is typically, I guess the answer is both, but typically rupture discs are custom made. That's because most installations or applications are unique. I'd say unique in terms of size, pressure, material, process medium, materials of construction, etc. Even what we like to call manufacturing standard could be unique.
I suppose there are some industries that can have stocked or pre-made rupture discs. A couple that come to mind would be the rail car industry. The rail cars are governed by codes that dictate what settings and styles of relief devices there are. Another one might be the specialty gas business on the back of some of the trailers.
Also the extrusion business. They just have nominal pressures. So.
Yeah. So I guess the answer is yes and no.
Yeah, typically, the answer is the rupture discs are custom made. Each installation is typically unique, but there are some industries that have stock pressures. I hope that answers the question, Scott.
All right, great. Thanks. Yeah, thanks for that. All right, we're going to move to the second question. We mentioned leak tight during your presentation. So are rupture discs, the question is, are rupture discs actually leak tight?
Great question. Leak tight is all relative, so we need to give it a frame of reference. And I like to use the term bubble tight, because people can identify with a bubble raising in water. So most rupture disc assemblies would be designed to be leak tight in that frame. That being said, we can manufacture products, and some standard products can be made to much higher leak tightness levels.
Yeah, leak rates are an engineering discipline all on their own, but suffice to say, all rupture disk manufacturers should be able to tell you the leak performance of the style of assembly that you are selecting or that they're recommending. We here at ZOOK use helium leak detection equipment to validate and state what our leak rates are. And we could probably send some information out to answer that question directly if we'll have their email address. But suffice to say that all rupture disk assemblies are leak tight, some more than others. Obviously, a threaded joint is less leak tight than a bolted joint, which is less leak tight than a welded joint. So if leak is a critical requirement to your system, I can think of a couple industries. Aerospace has very exacting leak requirements. Vacuum service, things that are used normally in vacuum, have very specific leak requirements. And you need to let your manufacturer know those things ahead of time so they can supply a design that's been tested and certified to perform at that level.
Yeah, just one more comment there. For flange connections, the installation of proper gaskets and proper torque, as Cam mentioned earlier in the presentation, is a must. So it's not just the joint where between the disc and the disc holder. It's between the device and the piping that also. So I hope that answers your questions.
Yeah, that's good. Thank you. That's good. Excellent. So we'll move on to the next one. The next question is the following. I've been told that I can still install a damaged forward-acting rupture disk. Is this true?
Well, that's a difficult question to answer. The safe answer for us here at the factory is to say no, never install a damaged rupture disk. Reverse-acting disks, by their nature, because they're virtually an arch, for lack of a better term, will collapse or burst at a level well below their marked level if the dome is damaged. I suppose the tension-loaded or forward-acting disks are typically less affected by damage in the positive direction, but suffice to say, a damaged disk will most certainly have a reduced service life, I guess.
Yeah, forward-acting disks typically are what's known as fail-safe, and that the worst thing that can happen is they'll relieve below their marked rating.
Yeah, I suppose if you have a lot depends on the actual operating conditions. Even a forward-acting, if you have vacuum and or back pressure in your system, it's probably going to collapse and for sure reduce service life. So the easiest answer is to say no, please don't install one. I hope that answers, Scott.
Okay. Yep, that's good. All right, let's move to the next question here. So the question is, how can I tell if the holders in my facility are pre-torqued? And can I change out my holders with pre-torque style?
Great question. Well, it's actually quite easy to tell, because for a pre-torqued holder, you have to have some cap screws present to provide the torquing. And I got to say, these cap screws aren't your standard run-of-the-mill cap screws that you can get at Home Depot. They're a high-strength alloy that can provide the available clamping load to the disc. So how can you tell? If you've got these cap screws in the holders, they're probably pre-torqued holders.
Yeah, if the manufacturer is specifying a torquing load, well, first of all, I guess if there's a vertical bolting assembly to your holder and there's a recommended torque level, it's more than likely a pre-torque holder. That's the best way. Typical insert style holders mostly just have little tabs on the side connecting the inlet and the outlet. And the assembly isn't, in effect, vertically loaded, for lack of a better term.
Yeah, the tabs are really just used for handling.
Yes, yes.
Right.
Yeah.
And the second part of that was, can I change my holders out with pre-torque style? And the answer there would be, well, yes and no. Typically, if it's an existing installation, your existing holder would have a certain height to it, what we call in the industry a face-to-face dimension. Basically, typically an insert holder, because it doesn't require a vertical load to seat it, they're often thinner than the minimum height you can get with a pre-torque, because the pre-torque loading requires a certain mass to the holder to take up that load. So What you need to do is either measure the height between your flanges or know the make and model of the holder you've got, and anybody you contact will be able to tell you whether their pre-torque holders can be modified or be supplied as standard to fit your existing opening.
Yeah, I've got one other thing on the part one of that question. Most pre-torque holders aren't round.
Yeah, fair enough.
Okay, they're the outside shape of the holder has to be modified to accommodate the pre-torque bolts. So if you've got a strange shaped holder, it's more than likely pre-torque.
Yeah, I think that, yes.
Yeah,
that's it. I hope that answers the question, Scott.
Yeah, that makes sense. Thanks. So, all right, let's go to the next one here. So the next question is, do all rupture disks work in both gas and liquid applications?
Well, the answer there is no. Each manufacturer will have disk designs that will work in either liquid or gas or both, but not all designs can work in both. Some, as Scott mentioned earlier when he's going through the disk models, some reverse acting designs need the expanding energy of escaping gas to kind of drive the disk open and basically to create the required MNFA. So you'll need to specify the process medium to the disk manufacturer when you need your installation. They'll be able to provide you a proper disk model.
Yeah, I mean, if you think of it, you know, the stored energy in a compressed gas is huge, whereas the stored energy in a peanut butter jar is not much, and the disk needs to be designed to react accordingly. Hopefully that answers your question.
Okay. Yeah, that's good. All right, so let's move on to the next one here. So the question is, are there pressure or temperature limitations to rupture disks?
Great question. I was hoping someone would answer that because people often forget about the effect of temperature on the pressure relieving device or the rupture disk. So absolutely, there are temperature limitations and there are effects of temperature on a rupture disk. Rupture disks are made of either graphite or metal, and these materials all have absolute min-max pressure ranges that they can safely operate at. This can be used or considered during rupture disk selection as well. And temperature also affects the bursting pressure of a rupture disk. Typically, adding temperature will lower the burst pressure. Removing temperature will increase the burst pressure.
Yeah, so getting back to the first question, I think, which was about stocked burst pressures or standard burst pressures. Those are standard burst pressures, but the temperature will ultimately affect what pressure the disk will burst at. And as Scott says, the higher the temperature, the lower the pressure and reverse. So yes, there are absolutely temperature limitations to all rupture disks, and it's typically a function of the materials of construction.
Yeah, another point that during the manufacturing process or the lot qualification process, the disks are burst tested at the coincident disk temperature or the burst temperature that's specified by the customer.
Yes, so when we do our lot qualification tests, we will test them at the pressure and temperature that they're marked at. So hopefully that helps out.
Good. Yeah, that's good. So we have about 1 minute left, so we're gonna right before we wrap, we're just gonna try to squeeze in one more quick question here. So the last question is going to be, are there sensors available to indicate a rupture disk has activated?
So the answer there is yes, absolutely. I believe all rupture disk manufacturers provide various forms of sensing devices that can be used to indicate to controls or equipment that a burst event has occurred. These vary from what we call integral or independent devices, some utilizing proximity switches or simple mechanical strips that break, but all interrupt a circuit typically that would be connected to control equipment.
Yeah, it's interesting, this question, because the indication has to be selected in the same way the rupture disk design has to be selected. You've got to consider the flow medium. You have to consider the upstream and downstream conditions. You have to consider temperature.
Hazardous environment.
Underwater. So it's not quite that easy to select the right indication.
Yeah. Once, I guess the moral story, getting back to the theme of the whole thing, it's a collaborative effort. Give your rupture disk manufacturer every piece of information you possibly can, because it'll help them engineer the best solution possible for you.
Right.
So.
Excellent. Thanks. All right, so we've actually come to the end of our webinar here. We had a large audience today, and so a lot of questions came in. We don't have time to get to all of them, but all of the questions have been captured, and the speakers will be looking at those and following up where they can on the questions that have been answered, or rather asked, that we didn't have time for. So before we wrap up, I just want to thank the speakers again for sharing their expertise today. And also, I want to thank our sponsor for today's webinar, that's ZOOK. ZOOK's a leading manufacturer of high-quality metal and graphite rupture disks and other pressure relief products, and their sponsorship has allowed the program to be viewed free of charge today, so thank you. And just a reminder that if you would like to view the webinar again, you can go to www.chemengonline.com/webcasts, and you'll be able to view the webcast again. And there's also going to be a link for event resources where you can find the slides. And I am informed that ZOOK will be actually sending the slides and videos out to the registrants as well. And ZOOK will also have the archived version of the webcast at their website. It's zookdisk.com, all one word. So with that, we're going to wrap up, and thank you to all the attendees today, and we wish you all a good day.